So when we've talked about absolute value, I've told you that anytime we're going to look at it, we have to have a piecewise function because none of our rules apply. We don't have rules for the absolute value itself. So we've always rewritten it as absolute value of x. And if you put in a positive, the absolute value doesn't change it. But if you put in a negative, it gives you the opposite because absolute value just makes your number positive. So let's take a look. Really I want to look at three different things. I want to look at when x is greater than 0, when x equals 0, and when x is less than 0, and see if we have a derivative in all of those situations. So I'm going to start first when my x is a positive number. Then the derivative, using our definition, is the limit as h approaches 0, f of x plus h. So if it's positive, we're on the first piece, so that's just x plus h, minus f of x, which would just be an x, over h. What happens? As x's drop, I get h divided by h, which is 1. Okay, so we definitely have a derivative. This is differentiable when my x is bigger than 0. We do get a derivative. It is equal to 1 in that case. Okay, second case. Let's go to when x is less than 0. So then our derivative be the limit as h approaches 0. F of x plus h, this time we would be on the second piece. So be a negative x plus h, minus f of x be a negative x over h. So then you get a negative x, a negative h, and a positive x. Positive x and negative x cancel. Negative h divided by h is negative 1. So it's differentiable for x is less than 0. Okay, but here's the thing. What about 0? Because technically, if you're thinking about the piecewise, shouldn't 0, if I included 0 with my first case, I would get the limit equals 1. Couldn't you just as easily have said that the absolute value is equal to negative x if x is less than or equal to 0? If I plug a 0 into this bottom piece, shouldn't it still work? If I put 0 in the top, absolute value of 0 is 0. Positive 0, negative 0, those are the same things. But these limits turned out to be two different things. Okay, what this is showing me is the limit as we approach, I should say h, approach 0 from the left. Sorry, I said left and wrote right. So from the right of my function turned out to be 1, and the limit as you approach 0 from the left of your function turned out to be negative 1. These pieces are different, so that means it does not exist at x equals 0. So this one is not differentiable at 0. It might make a little more sense if we look at a graph. If we graph the derivative, we said the derivative is always 1 if x is bigger than 0. So that's just a horizontal line. It's always negative 1 when x is less than 0. So can we see then those pieces don't match up, so at 0 the derivative doesn't exist. so the question is, what makes it not exist here? What about the absolute value function? I mean, clearly we worked it out, and I gave you an explanation for why, but it would be nice if we could know that sooner, rather than doing all that work. So a couple things that we're going to mention, and then we'll get into the three cases where your function will not be differentiable. One thing that we will know is if it's differentiable, it has to be continuous. So anytime the derivative exists, the original graph had to have been continuous. That's part of the reason we talked about continuity in this. So what that means is if it's not continuous, the derivative doesn't exist. So anywhere there's a break in your graph, you will not have a derivative. It is possible for the function to be continuous and the derivative to not exist. So just knowing it's continuous doesn't guarantee there is a derivative, but knowing it's not continuous guarantees there is not a derivative. Does that make perfect sense? Let's look at it in terms of a graph. So the first situation we saw, the absolute value wasn't differentiable at 0. What does it have at 0? Yeah, what's formed on my graph right there? What's that? Yeah, it was that vertex. But it's different than in a parabola where it's a nice smooth one. Here it was a corner. Anytime you have a sharp corner, the derivative doesn't exist. Keep in mind, the derivative is the slope of the tangent line, right? If you have a sharp corner, is there only one tangent line you could draw there? No. If it's a sharp corner, there are an infinite number of tangent lines that would hit that and bounce off right there. So anytime you have a graph with a corner, it's not differentiable there. Okay, that's the first case. Second case, we said, I just got done telling you that it has to be continuous to be differentiable. So if it's not continuous, it's not differentiable. If you have a break in your graph, can you draw a tangent line? No, so it's not differentiable there. Third case is when you have a vertical tangent line. Because at a vertical tangent line, a derivative is the slope of a tangent line. What's the slope of a vertical line? Undefined, so the derivative doesn't exist. So, three cases, vertical tangent lines, and again, that's because it's just difficult to draw that one unique line. The vertical line has an undefined slope, and this is another case where your tangent line would be vertical. The corners, the discontinuities, the vertical tangent lines. This tells you the three things that cause the derivative to not exist. So I think some of your homework has you just looking at a graph and telling where the derivative doesn't exist, and that's what you're looking at. Is there anywhere where there's a break in my graph? Is there anywhere where there's a sharp corner? Or do we have a vertical tangent line? Any questions here?
No.
All right. Let's go ahead. We're going to talk about higher derivatives next. So we have been finding the first derivative, but we could do the second derivative, the third derivative, and as long as we want it, we can repeat this process multiple times. Notation-wise, when you see it want a second derivative, they usually write it like this. Put a d squared y over dx squared. That's just notation for second derivative. I might also write it as, I will typically do f double prime or y double prime, so most often I'll use one of the second two notations there. All of those are just saying do your derivative 2 times. So yesterday, I think we did, okay, looking back to example 2. We did the derivative of x cubed minus x. So from yesterday, in example 2, what did we get for our derivative? I believe it was 3x squared minus 1. So if I want the second derivative, we repeat this. So we do the derivative of that first answer. So that's the limit as h approaches 0. F of x plus h. So this is my function now. Minus f of x, which we're using the first derivative for our function, divided by h. Okay. So if you square that, and then if we distribute, we get 3x squared plus 6xh plus 3h squared minus 1 minus the 3x squared and plus 1 divided by h. Okay, then 3x squared and negative 3x squared cancel. Negative 1 and positive 1 cancel. I can divide an h out. So I get 6x plus 3h. Then if I plug in a 0 for my h, that just gives me 6x. So this second derivative was actually a little bit faster to calculate than the first derivative here. That's typically the case if you have a polynomial that as you do repeated derivatives, it does get a little bit shorter each time. Not the case with every function. If you're dealing with radicals and things, sometimes when you go to do the second derivative, it can get a little bit nasty. But with these polynomials, typically higher derivatives get nicer. So, what does this mean? The first derivative gives you the slope of the tangent line, right? So the second derivative would be the slope of the tangent line of the graph of the derivative. What it's telling us then, it's going to give us the rate of change of the slope of the original. We will be talking about this a lot. In the next chapter, we're going to learn some shortcuts for derivatives. And we'll be talking about what the first derivative tells us on a graph, what a second derivative tells us on a graph, and those things. If we think about like physics, we have a position function. If you take the derivative of position, so if you start with position, derivative would be the rate of change in your position. What is that telling me? How the position changes. The first derivative is velocity. You're starting with position. If I want to know how your position changes, that's velocity. It's like your speed with direction. It tells us if we're going forward or backward. Okay, if I want to know how your velocity is changing. Okay, so position, I'm starting at school, and I'm going to drive to Hannibal. My velocity at a given point is telling me the direction and my speed. If I ask you how my velocity is changing, what am I asking you for? Is your speed always the same? No. when I ask, you know, are you speeding up, are you slowing down, that is your acceleration. So that second derivative is giving me the acceleration. It's telling me how my velocity is changing. You know, a positive meaning I'm speeding up, a negative would mean I'm slowing down. Third derivative, I don't talk about it very often, and actually probably after today we won't ever talk about this. We'll just really focus on position, velocity, and acceleration. Do you guys ever talk about jerk in physics? In math physics? Okay. I didn't think, from previous years they told me that they hadn't really talked about that, so I kind of focus on just the first three. But if you're talking about how your acceleration is changing, that's actually referred to as jerk. So there are applications for these higher derivatives. It's not something I just make up to make you do derivatives over and over and over again. They do have a purpose. So second derivative, I told you I'll put like 2 tick marks. Third derivative, you can do 3 tick marks. Typically after 3, instead of putting tick marks, we just put the number. Now if I were doing the 5th derivative, I don't want to write 5 tick marks up there, so you would just put your little number if you wanted a higher derivative. So let's do a third derivative and the fourth derivative. So this is the function that we were already using. So in example 2, we did the first derivative. In example 6, we did the second derivative. So from example 6, my second derivative was 6x. So my third derivative, bless you. Alright, so I have to do the derivative of my previous answer. So that is the limit as h approaches 0, f of x plus h, so 6 times x plus h, minus f of x, just 6x over h. So we get 6x plus 6h minus 6x all over h. What happens? 6h. And 6h divided by h is 6, so we get 6 for the answer. If you have a limit of a constant, it's just that constant value. So the fourth derivative, I did the derivative of this. That would be the limit as h approaches 0. F of x plus h, do I even have an x to plug it in here? So f of x plus h is just 6, minus f of x is just 6 over h. So I get 0 over h, which is 0. That's a constant. Derivative of a constant is that constant. So my fourth derivative here was 0. And once you hit that point, any further derivatives will also be 0. So 5th, 6th, 7th, everything from here on out would be 0.
How did you get 6 again on the top?
So my 6x's dropped out. Then I had 6h divided by h, so I canceled my h. And then a limit of a constant is just the constant.
Sorry, my bad. But the,
Oh,
the
right
6
here.
minus, yeah.
So f of x plus h says go to your function, plug in x plus h in for your variable.
Okay.
There is no variable, so it's just the same.
Okay. Alright, thank you.
You're welcome. Anything else? Okay. So that is all of the content The rest of the stuff that I have on here are more sample slides, like some of our homework problems. So we'll do maybe a few of these together. We did number 1 on your homework yesterday. Well, let's do number 2, another one like that, because I know 1 was a struggle. So more practice is always better. All right. So f prime of 0 means you have to draw your tangent line at 0. Now I struggle with this a bit, trying to draw a straight line up here, but give it your best shot. So a tangent line hits it at that point. You might need to use a sheet of paper to kind of draw that straight line. We are approximating here. We don't have this down to a science by any means. And then we need to calculate slope here, so rise over run. So if I just took these points, I would go up 2 over, I don't know, do you think a third? So 2 divided by 1/3 is 6, yes.
I have a question. So like when you plot your other 2 dots, are you just always put on the line?
Yeah, I'm just trying to pick points that I can find easily. You can take any 2 points on that line. Okay. F prime of 1. So if I go to 1, oh, that's not, when my x is 1, sorry. That would be right here. So your tangent line would be horizontal, so that one has a slope of 0. That's an easy one. We should all be able to get that one. Okay, when my x is 2, I'm right here. Even if you have nothing else, you should know, is this one going to be positive or a negative slope? Negative, because my graph is decreasing there. Okay, so if I try to graph this to the best of my ability, so just trying to draw it. Okay, pick 2 points, so here I would go up 1 over, I go back, what do you want to call it, 0.7?
Yeah.
So that would give us what? About 1.4. We're not real precise here, just kind of close. All right. F prime of 3. So when my x is 3, would this one be a positive or a negative again? Negative, okay. Should it be, do you think it'll be higher or lower? Is it more or less steep than the one we just did? It's kind of less steep there. Okay, so if I just take these 2 points, I would go up 1 and backwards, what do you say, 0.5, 0.6, 0.6. So I left off my negative on the previous one. And that gives me about a negative 1.7. So we're not real precise, but we're getting close. That's all I'm asking for here. F prime of 4. So my x is 4. Okay, looks like this is kind of leveling out a little bit. If I take 2 points, rise over run, looks like I go up about 0.5, backwards -1, so we get a negative 0.5. F prime of 5. 3,
Yeah.
and backwards 1, so we get a negative 0.3. F prime of 6. What would you call that one? 0. F prime of 7, should this one be a positive or a negative? So if we try to ballpark that, maybe go up 0.3 over 1, and we get 0.3. Emily, did you do all right? Okay. Do you have any questions? Okay. Okay, so then if I asked you to draw the derivative here, you are just plotting all of these values. So the first one we started at 6, which my graph doesn't really go high enough, but okay, so it's gonna be way up here. I can't scroll up any higher without moving everything. When I'm at 1, we're at 0. 2 is negative 1.4, negative 1.7. I'm not 100% sure that those points are great, but it gets us the ballpark anyway. 4 is negative 0.5. At 5, we're at negative 0.3. 6, we're back at 0. And 7, we're at 0.3. So we're using that to kind of sketch the derivative. I'll be honest right now, I'm probably not going to give you one like this on the test. What I would be looking for is more like something that we did on the questions after that. So I think I assigned like 3 was matching, which I could do something like that. Then we got into the ones where you had to draw the derivative from the graph. So I might do one of these on a test. So same idea, but a little less formal. So here's my graph. If I want my derivative, where would my derivative be 0? Right, anywhere you have a maximum or a minimum. So when x is 0, my derivative will be 0. You'll notice here, your graph is flattening. That means your derivative is not ever exactly 0, but it's going to get smaller and smaller, so that's going to kind of act like a horizontal tangent line. This part of my graph is increasing, so what does that tell me about my derivative? It's positive. So we have to have a positive derivative, but then it kind of starts to taper off and it's just getting closer to 0. So something kind of like this. It's still positive, but it's flattening out. It's like that horizontal tangent. Then this section is decreasing, so my derivative would be negative. Again, as time goes on, this is flattening out, so my derivative will get closer and closer to 0. So this derivative would look something like that. So that's like questions 5, 7, 9, all of those on there. Problems 13 and 15. I'm going to do a sample one like that. So we're going to do problem 14 out of the homework. So this graph shows how driving speed affects gas mileage. The fuel economy is measured in miles per gallon and speed is in miles per hour. So part A, you're telling me in words, what is f prime of v? So a derivative is always the rate of change okay. Then it's the rate of change of the Y value. The miles per gallon, that's your gas mileage. And then it's in terms of your X, which was your speed. Okay, a derivative is just like a slope of a tangent line. Slope is y over x, so it's always going to be the rate of change in y with respect to x, or in terms of x. So it's telling us how the gas mileage changes with respect to your speed. All right, sketching the graph. So anywhere, do we have anywhere where the derivative would be 0 here? Anywhere would we have a horizontal tangent line? Yeah, probably roughly 60. Okay, I don't know, it's kind of in the 50 to 60 ballpark, somewhere in there. Maybe, I'm going to call it more 55. We'll meet in the middle. Okay, up to that point, my derivative starts out, it's always increasing, so we know it's always positive. Starts out increasing pretty quickly, so that means your derivative would be a higher number, because the slope is steeper. And then it kind of flattens out, so your derivative would be getting closer to 0. So without finding exact slopes, it's something like this. And then what happens after that? Decreasing. Okay, so something like that. So basically what that's telling me is up until I hit 55 miles per hour, the faster I go, the better fuel economy we're getting. But after you hit 55, going faster is actually decreasing your fuel economy. All right, so part C, at what speed should you drive if you want to save on gas? 55 miles per hour. That is our optimal speed. So far, so good? We're going to go ahead and do the last two. And then you'll have some time today and probably, maybe not a full class tomorrow. I might introduce the next section, but a good chunk of class tomorrow to work on this. We'll kind of see how it's going. So then, on your homework, you get into ones where it's asking you to look at a graph and tell you where it's not differentiable. So where does the derivative not exist? So remember, things that make it not exist would be sharp corners. Does that happen anywhere? 3. So x equals 3, and my reason would be the corner. Okay, discontinuities. Do we have any breaks in our graph? At 0. And the third scenario is a vertical tangent line. Would we have any vertical tangent lines? Yeah, it looks like at maybe 6, which our graph kind of ends there anyway, but that appears to be vertical tangent line. So this graph would have 3 situations where it's not differentiable. Is this helping to kind of work through a sample problem with all the different things on here? So last one. I've given you 4 graphs here. One is the function, one's first derivative, second derivative, and third derivative. We need to figure out which is which. So this is kind of a daunting task to begin with. Some suggestions. I usually try to start with the most complicated graph, like the graph that has the most changes in direction to it. So the most maximums and minimums. That's not guaranteed to be your first one, but it's a good starting point. So which one would that be? D. Okay, so let's start there. All right. So D would have a horizontal tangent line here and here. So its derivative would have to be 0 at those places. So which one is 0 at both of those places? C. Up until that point, D was increasing, so the derivative is positive. Then it's decreasing, so derivative is negative. Then increasing, so derivative is positive. So C matches. So C has to be the derivative of D. Okay, so now let's look at C. Where would it have a maximum or a minimum? So at 0. Okay, so there's really 3 options. We know it's not D because we've already used it. So it's either A or B. Until that point, our graph was decreasing, so the derivative had to be negative. After that point, the graph was increasing, so the derivative is positive. So which one has to be the derivative of C? B, because it needs to be negative first, because we start out decreasing. So it has to be, the derivative of C has to be B. Okay, so now we need to look. A is the only one left. Either A is the derivative of B, or A had to be the first function. Okay, so let's check. If we find B, where would it have a horizontal tangent line? Just right there at 0. This graph is always increasing, so the derivative should always be positive. Does A match that? Yes. So that means D was the first, or the original function. C would be the first derivative, B the second derivative,